2009 EC4. So we have a differential equation here given. It says dy dx is 6x squared minus x squared y. And f is a particular solution. The initial condition they give us is that f of -1 is 2. And from there, our first job here is to use Euler's method with two equal step sizes starting at x equals -1 to approximate f of 0. And we're going to show our work that leads to our answers. One thing as an aside here is that some of you, we've done 5 or 6 Euler's method problems in this AP stuff. And some of you guys don't even know how to start it at this point. Okay? That's not okay. I guess if you just want to give up 2 or 3 points on the problem, you can bank on the fact that it's going to be on there. If you don't bother to do anything with it, you can pretty much bet it's going to be on there. So ultimately, in the scheme of things, all this is a linearization. Okay? If you start out with your your first f of 1 equals 2, and we're going in 2 steps. We're going from -1 back to 0. So we're going -1/2 and then 0. And ultimately, we're just going to get the initial y value. Okay? So if we want our approximation for f of -1/2, if you will, okay, we're going to start at the initial, and we're going to add to that okay, the derivative times the change in x. And in our particular case, the change, or the derivative, I should say, if we put a -1 and a 2 in here, we're going to get -1 is going to give us 6 here. A -1 here and 2 here is going to give us 2 here. So the derivative ultimately is 4. And then the change in x, in this case, is going to be, the change in x is going to be 1/2. Okay. All right. And if we figure that out, 2 plus 2, we get 4. And if we go to the next one, which is just f of 0, and we're only going 2 steps, so we just got to go to -1/2 and then 0. Remember, we're starting at -1 and we're going to 0. So that means that our initial here at this point would be the previous one that I just found, which is 4. So the next y value at -1/2. We're going to add to that the derivative times 1/2 again. So here we need to find the derivative. Keep in mind that the derivative is going to be found at the -1/2, 4 point this time. Now we use the next. We use -1, 2 in the derivative to find this one. We use -1/2, 4 in the derivative to find this one. Again, we find the next y value by using the derivative at that particular point we're at right now. So if I put a -1/2 in here, I'm going to get, ultimately I'm going to get a quarter in here. So it'll be 6 times -1/4, which would be -3/2. And then minus, and this would be -1/4 here times 4 here. And with that, we'd have -3/2 plus 1. And so we get -1/2. I did the math on that, right? Yeah, we got should they have plus or minus sign somewhere? Negative, positive. You got 1/2 in here gives us 1/4, right? Oh, it's positive. That's why. That's why. And then the quarter is negative. Quarter is positive also, so it's just minus. So it's ultimately positive and then -1. So it'll be positive 1/2. There we go. Sign straight. So, and if we do that, we're going to wind up with 4 plus 1/2 times 1/2 is 1/4. So we'd ultimately get 4 1/4. And 2 points for that. Ultimately, our final answer is this one, so point for that. And then just the fact that you used the Euler's method properly. Using your, again, initial y value plus derivative times initial x value. Okay. And then new y value that you just found, derivative at that new point, times change in x again. Okay. All right. 2 points there on that part A. Questions? All right. Then on part B, says at the point -1, 2, the derivative is negative. The second derivative, that is -12. And we want to find the second degree Taylor polynomial for x, for f, that is at x equals -1. Alright, so ultimately we know that the Taylor polynomial can be found by using the derivatives, the function, the derivative, second derivative, and so on. That's how we build a Taylor polynomial in general. So ultimately, we know that this first one is going to be f of, normally it's f of 0 if it's Maclaurin series, but this time it's not centered at 0, so we need f of -1 because that's the point in question. So that ultimately is going to be 2. And then we know that the derivative at the derivative of this function is the differential equation they gave us. So at -1, we determined that was 4 earlier. That's what we found that right there a minute ago. So that's going to be 4. And then remember, if this is centered at x equals -1, then we need to have, instead of just x, it needs to be x plus 1, just like any translation. And that's going to be that linear part. And then the quadratic part, if we figure out the second derivative, we know the second derivative is -12. Okay. And so we could add to that -12, and then here x plus 1 squared over 2 factorial, which ultimately the 12 over 2 factorial reduced to 6. 2 plus 4, x plus 1, 6, x plus 1 all squared. That would be our Taylor polynomial worth 1 point. Alright, questions on part B?
Do you have to reduce the factorial if you do 12 over?
I wouldn't take chance on leaving it like that if it's reducible.
Okay.
It's hard to say. I haven't seen any of the student examples where they marked that either right or wrong. So I don't know if I've seen one where they left it like that, something like that. I would suggest, like I said, since it's something simple like 12 and 2, I would do it. Alright, on part C, we had to just solve the differential equation, which is a 6-point problem. So you guys did some interesting stuff on this, but bottom line here is we need to separate variables. Okay, what's the first thing we should notice about this differential equation? What do they have in common? They both have x squared. So if we did dy dx, and we did x squared, and then 6 minus y, we bring the 6 minus y over here with dy and have x squared dx on this side. That's really the only way to separate these variables. I mean, ultimately you got two pieces, one has an x only and one has an xy, so if you're going to get them separated, you need to take that x term out. And if we do that, then answer here, and so I'll give you the points as we go. If you separate the variables properly, you get a point. And finding the antiderivatives, we know that this is, since this y is linear here, it's just going to be natural log. So, and ultimately, remember the chain rule here comes into effect because the derivative of this is -1. So that means it's going to be negative natural log of absolute value of 6 minus y over here, and x cubed over 3 plus c over here. 2 points for that line if you anti-differentiate it correctly. Alright, and then the having the constant of integration was another point. So, I'm sure you got c on there. Finding the value of c is worth another point. So the initial value here, remember, was -1, 2. So if we go 2 in here, and -1 in here would give us -1/3 plus c. Alright, and if we add 1/3 to both sides, we'd have 1/3 minus ln4 equals c. There's our c value, and again, another point for finding the c value. And then if we go back to our original, which is that, space here on my paper. So we have that as our equation. Ultimately, solving for y is going to be the last part here. So we can do division here by -1 first. We do negative x cubed over 3 minus 1/3 plus ln4. Divided everything by -1. Oppose both sides with e, we get 6 minus y over here. we're going to get e to this whole thing here. And I'm going to separate those into different parts immediately, because ultimately if I add e to that stuff all added together, and that's the same as e to each one separately being multiplied. And that would do me good because e to the ln 4 is simply 4. So we get 6 minus y, 4. Really nothing we can do with these two, so I'd probably put it back into just one e sentence. Which is that. And once we have the natural log part out of there, we can subtract 6. And then divide by -1. So final answer then should have been -4 e to the negative x cubed over 3 minus a third plus 6 on the end. And one final point for getting that correct. Okay, questions? Why was it minus?
No, over here. Yeah.
Over here?
Yeah.
Remember when we do this 6 minus y, ultimately if we let that be u, our du here would be -1 dy. Okay. In order to perform this integral here, okay, to get rid of dy with our du, we'd have to put in -dy. Remember the chain rule here, this is got a -1. I mean, if this is y plus 6, we've had to worry about that. Ultimately, that's because the derivative of this is -1. So going backwards, if we were to differentiate this, if we just had ln of this, we'd go 1 over that times the derivative of that, which is -1. And ultimately, that other negative would cancel it out and make it back to positive, which is what we have here. Good question. What else on that one? All right, let's take a look then at the next one here. We have number 5. And in number 5, they give us a table of values here for function and just the function only, I guess. And so it tells us that f is a twice differentiable function. The table gives values for -2 to 13. Well, it's a closed interval, keep that in mind. And part A here says estimate f of 4. So in part A, we have the point 34 and we have the point 5, -2. So if we want to estimate the derivative at 4, we'll just find the slope here. So it should have been -2 minus 4, 5 minus 3, and -6 over 2, which would be -3. So 1 point for that, for estimating the slope with your work. Okay, part B says that we want to evaluate 2 to 13 of 3 minus 5 f prime of x dx. Alright, so again, we're just a property of integrals problem. I mean, it looks like it might be complicated here, but ultimately if we separate this and break it into 2 to 13 of 3 minus, and break out the 5 here, 2 to 13 of f prime, separate it into 2 separate integrals here, factoring the 5 out so it's a constant multiple. Then this one, what's the antiderivative of 3? 3x. And 5 out here, and what's the antiderivative of f prime? F. And with that, we got this piece will be 20 or 39 minus 6 would be 33. And then in the parentheses, we need f of 13. What's f of 13? According to the table, f of 13 is 6. And then we put in a 2. What's f of 2? That would be 1. So we wind up with 33 minus 25, which is ultimately 8. 2 points. One for using the fundamental theorem, so finding the antiderivatives, essentially. One for getting 8. Any questions on that one? Okay, part C we have to use the left Riemann sum with subinterval indicated in the data to approximate the area under the curve of f of x and show your work. Ultimately, if we're going to use a left Riemann sum, okay, you'll notice that the intervals here are not uniform. Okay? So we're going to need to deal with each of these separately. But ultimately, we're starting at the point 2, 1. Okay? And then we're going to the point 3, 4. And then we're going to the point 5, negative 2. And then we're going to the point 8, 3. And then 1, 2, 4, 5, 13, 6. So we're going to do a left Riemann sum, where the first rectangle is going to be drawn at the left end point and over. Okay. So left end point is height, over to the right to the next interval number, which is 3 in our case. And so ultimately that would be 1 by 1. So that one would be 1. The next one, if we draw it from this height over to here, it's got a 2 here, and it's got a height of 4. So 2 and 4 would make 8. Third rectangle, we draw down to this one, and then across over here to this one. And distance-wise, we're going from 5 to 8, so that's 3. Height-wise is 2. And so 3 times 2 is 6. Of course, it would be negative 6 because it's below the x-axis. And then the last one would be from here over to here. And that would be 5 by 3, 15. And ultimately, if we add those up, we're going to get, 24 minus 6 would be 18 total. So 2 points for using a left Riemann, 1 for using left Riemann sum, 1 for the answer. Questions? Okey-doke. Let's take a look at the last one then, part B. We are asked for, it says, suppose that f prime at 5 is 3, f double prime is less than 0 on the closed interval 5 to 8. So that means that the derivative is positive, and the concavity here would be concave down since the second derivative is negative. And so just for, without even doing anything else here, just to kind of think about picture-wise, we got a positive derivative, concave down, so maybe something like that, essentially. True? So between 5 and 8. And we know it's going from 5, negative 2 to 8, 3. And we know the derivative at 5 is 3. So here we have a slope of 3. Okay. So that's kind of what we're dealing with here. So let's see if we can figure out then. It says to use the tangent line of the graph of f at x equals 5. So to use that, we need to find it. So let's find it first. So we know y minus y1 and m times x minus x1 is going to be our starting point. All right. So the tangent line to the graph at x equals 5, that means that 5 and negative 2 are going to be our x and y in question in the equation. And we know that the tangent line's slope is 3. Our derivative at that point is 3, it says. All right. And ultimately, the question says to use that tangent line to show that f of 7 is less than or equal to 4. So f of 7 is less than or equal to 4. And again, I got kind of an exaggerated picture here, but bottom line here is this tangent line had better be above the curve, shouldn't it, since it's increasing in concave down. So if we could take our tangent line, like it asked us to do, use the tangent line to show that f of 7 is going to be less than 4. Okay, if we take our tangent line here and we go 3x minus 15 and minus 2 would be minus 17. If we were to put a 7 in there, what do we get? We get 4. So that means that the line at 7 is 4. So what does that tell us about the curve at 7? The curve would have to be less than 4, wouldn't it? Okay. But again, the justification here, though, you need to tell why. Why is that? Because we know that this function is what? It's concave down. So that tangent line is going to give an overestimate for anything to its right. Okay. So So you need to talk about that. Ultimately, finding the tangent line itself was worth a point. Okay. Showing that it was less than 4 was worth a point. Okay. And again, part of this showing part is the discussion of the fact that since it's concave down, this tangent line is going to give a overestimate for the value of f of 7. Alright, and then the second part says use the secant line of the graph on 5 to 8. And the secant line on 5 to 8, remember, is the line that connects 5 and 8. Okay? Secant line is just the line that connects 2 points on a curve. So if we take those 2 points and we calculate the slope, -2 minus 3, and then 5 minus 8, get -6 on top and -3 on the bottom. And with that, we'd ultimately get, actually, not 6, 5, no, 5 thirds. 5 thirds would be the slope of that secant line. The equation for the secant line, we could use those same points, y plus 2 and x minus 5. So there's your secant line, worth a point. You found the equation for it. And then in the last part, it asks us to use that secant line to show that f of 7 is greater than 4 thirds. So greater than 4 thirds. Okay, again, same reasoning basically is the slope between these endpoints here, the line that connects the endpoints is always going to be, since it's concave up, or concave down that is, it's always going to be less than the function value in between, isn't it? So if we take our 5 thirds x, and this would be minus 25 thirds, would be minus 31 thirds. And we plug in our 7. We're going to get, what, 35 thirds? Minus 31 thirds. And lo and behold, it's that 4 thirds that they mentioned, isn't it? Okay. And again, why do I know that the function has to be greater than 4 thirds? Because if it's a secant line on an interval that's concave down, that secant line is always going to be what? Tangent line is going to be above the curve. The secant line is always going to be below the curve, isn't it? Okay. And you want to mention that information in there as well. Okay. All right. Any questions on any parts of number 5? Okay. Take a look at number 6. We have Maclaurin series given. And the Maclaurin series for e to the x is given. And they've given us a function to deal with here that's e to the x minus 1 all squared minus 1 over x minus 1 all squared. And our job in part A given also that f of 1 is equal to 1, it says here. And it says the function has derivatives of all order. And it says part A, write the first 4 non-zero terms and the general term for the Taylor series for e to the x minus 1 all squared. So bottom line is we have a Maclaurin series for e to the x, which is 1 plus x squared over 2 plus x cubed over 6, so on. And if we're going to write one for this new function, e to the x minus 1 squared, ultimately, if we take our original as stated and we replace the x with this, then we can replace these x's with this as well and get a new answer. So we'd have 1 plus x minus 1 squared plus x minus 1 squared squared, which would be to the 4th over 2, plus x minus 1 squared cubed would be 6 over 6. And let's see. Oops, there we go. So that would be the first 4 terms. If you got the first 4 terms, you got a point for that. And then the general term here, can we write a general term for this? We can see that the general term, we always have an x minus 1, and our x minus 1 is going to be to the 2n, because we have even powers here. And on the bottom here, our factorials are going to be, we have, this is 1, this is 2, this is 6. If we did another one, we'd get 24. Okay. All it is just n factorial on the bottom, isn't it? So there's your general term. Point for that one. Questions on that one? Alright, now on part B, once we have this established here, remember this is a Maclaurin series, or Taylor series actually, because it's not Maclaurin. This is a Taylor series for this function. Okay, so this and this are essentially the same on their interval of convergence. Fair enough. So if we're going to make a Taylor series for f, which is the given function up here, okay, ultimately, remember this part right here, we already have a series for that. True? Okay. So bottom line is, what do we need to do with this one that we already have to get this new one? We need to subtract 1, and then we need to divide by this. Okay, remember, that's what we're doing to get from this one to this one. Okay, we already have this one all set up. It's right here. Okay, all we need to do to get this new one is we need to take this whole thing and we need to subtract 1, and we need to divide by this. Okay, that's what we've done to our original Taylor series that we had in the first place. So let's see how that would look then. If I were to take some terms here, I'm going to take 1 plus x minus 1 squared plus x minus 1 to the 4th over 2 plus x minus 1 to the 6th over 6, and so on. Okay. And I take that whole thing, and keep in mind it goes to the general function, x minus 1 to the 2n minus, or over n factorial. And remember, I'm going to take that whole thing, and I'm going to subtract 1. So ultimately, if I take all that stuff and I subtract 1, then what's going to happen with these 1s? Yeah, those are going to be gone. So I'm going to do that right now, and I'm going to be, in my next step, I'm going to have that. I'm going to have that. I'm going to have that. And I'm going to have that still. Alright. And then ultimately, what am I doing besides subtracting 1 from all that? I'm taking and dividing it all by what? By this, by the x minus 1 squared. So if I take this whole thing and I divide it by x minus 1 squared, let's see how those terms are going to turn out. Well, this divided by this is going to be what? 1. So there's the first term. This divided by this is going to make this power go to 2. So it's going to be plus x minus 1 all squared over 2. This one divided by this is going to be x minus 1 to the 4th over 2. And then to get the 4th term, because they ask us for 4 terms and the general term here, we're going to need to figure out what this would have been over here, this next term. Not 2, but 6 there. No, 6. Thank you. Ultimately, the next term in our sequence, if we had kept going on this one, okay, would have been, if we would had x cubed, then the next one would have been x to the 4th over 4 factorial. So it would have been x minus 1 to the 8th over 4 factorial, 24. So that would be the next term up here. So keep in mind that that term is sitting right here now, right? So if we take that and we divide it, we're going to get x minus 1 to the 6th over 24. Alright, and so point for that. That's the first 4 terms. The general term here is going to be, again, similar to the other general term. It's going to be x minus 1 to the, in this case, it's we got 2, 4, 6 again. Still be 2n for that part. And then how about the factorial part here? Keeping in mind that by generating this, by letting this be 2n right here, we're assuming that this one has a 0 power to start with. So this is the 0th term. This would be term 1, term 2, term 3, and so on. Because a 1 in here would give us the 2, then a 2 in here would give us the 4, and so on. So bottom line here is that this is a 2 factorial here, okay? And really under here we have a 1. This would be 1 factorial. Question is, can we put just n factorial down here? Yeah, because if we put n factorial here, this would be a 1, and this would have to be a 1 also, because we're putting in a 1 here to get this term. So it would have to be n plus 1 factorial. Okay, 'cause again, this would be, if I were to put a 0 in, I'd get 1 factorial. If I were to put a 1 in here, I'd get 2 factorial. If I were to put a 2 in, I'd get 3 factorial, so on. So another point for that part. questions on part B? Alright, then the next part here for part C says that we want to use the ratio test to find the interval of convergence for the series that we found in part B. And again, the series that we found was x minus 1 to the 2n. So if I put n plus 1 in there instead, and on the bottom it's n plus 1 plus 1, so it'll ultimately be n plus 2 factorial down here. And we're going to divide that by the original, the n plus 1 factorial here, and x minus 1 to the 2n here. Alright, and remember with the ratio test here, we're going to try to manipulate this and then take the limit as n approaches infinity. So in terms of the factorials, this one is just 1 bigger than that one, because if this was, let's say, a 5, for instance, this would be a 6 in here, and this would be a 7 in here. So ultimately, these two could cancel out and leave us with just the n plus 2 on the bottom. And on top here, if I factor that, if I go ahead and do that, I'm going to have x to the x minus 1 to the 2n plus 2. And keep in mind that's x minus 1 to the 2n, x minus 1 to the 2. And then over here we have x minus 1 to the 2n still, which ultimately those and those would be gone. So with that we'd have x minus 1 squared over n plus 2. So that's the ratio test part of that, and then we're going to take the limit as n approaches infinity here. And ultimately what do we get no matter what x is here? Okay, what are we going to get on the bottom? If this grows, this doesn't grow, this is going to be some whatever it is. Okay. What happens if this grows? This is going to go to what? It's going to go to 0. And if you, from our ratio test, if that was less than 0, remember it converged. And find the test here. Maybe. The ratio test, remember the key information on the ratio test that we need to remember is that if that limit is less than 1, then it converges. It diverges if it's greater than 1, inconclusive if it's equal to 1. Okay. Alright, and so clearly we have our less than 1, which is good, what we wanted to have, okay, in order to show that this converges. Okay. Alright, and then ultimately the question asks finally what is the interval of convergence. Okay. So if the limit of this is 0, okay, the limit of convergence here is going to be all real numbers. So point breakdown here. 1 point for setting up the ratio test. So if you at least set up the ratio test, you get a point. Computes the limit of the ratio, in other words, finds this part, the point, and then the answer, point here. Liz?
Okay, say if you got B wrong, but you got C right for the equation you had in B, could you still get points for the...
It depends on how trivial it is. So if you got, a fairly legitimate answer, you were close, let's say, on part B, and then you did the right thing with that on part C, you could theoretically get those points. The problem is you can't like make something up that's totally off the wall for part B and say, oh well, I'll just use it for part C and call it good. So yeah, you can get points as long as you use something that's reasonable. Like I said, if I just made up some real easy series and did the ratio test, then that's not going to get us any points. Okay? But yeah, if you make a mistake in part B and you carry it through and you use that mistake, but you use it correctly and it's I guess of the same level, I guess, if you will, difficulty, then they're going to give you those points. Yeah. Okay, let's take a look at part D then, last part. We got says use the Taylor series for f that you about x equals 1 to determine if the graph has any points of inflection. So remember that that Taylor series, if we look back, was end up being 1 plus x minus 1 all squared over 2 plus x minus 1 to the 4th over 6 plus x minus 1 to the 6th over 24, and so on. Alright, and ultimately the what we need to consider here again is that if we use this Taylor series for f, which we did, which we have here, and we want to figure out does it have any points of inflection, then we need to ultimately look at the second derivative here. True? So if we figure out the derivative here is going to be 2 times x minus 1 to the 1 over 2, which would cancel and leave us with just x minus 1 for that part. The next part here would be 4 x minus 1 to the 3rd over 6. And then 6 times x minus 1 over 24 would be to the 5th. Simplify in a minute, but we may or may not need, more terms than this to decide, but ultimately we'll just use these 4 terms to see if we can figure out an answer. Derivative here would be 1, derivative there is 0. This next derivative would be 12 over 6, that'd be 2, x minus 1 to the 2. And then in this one we'd have 30 over 24, which would be 5/4, x minus 1 to the 4th, so on. Alright, and so bottom line here is if this is our second derivative here, we want to know if it has any inflection points. What has to be the case with the second derivative in order for us to have inflection points? It's got to equal 0. Well, what do we know about this piece and any piece beyond that that's going to have an even power? I mean, ultimately, the only thing that could make it 0 would be 1, right? And if it were 1, okay, the answer would be 1, which is not 0. True. And anything else that we put in here, no matter what, we're going to square it, raise it to the 4th, 6th, 8th, and so on. What's this always going to be no matter what? Positive. So therefore, what could be said? No inflection points. Again, f double prime is always greater than 0. That's 5. So 2 points, 1 for finding the second derivative. So if you actually found the second derivative and then analyzed, found the answer, 1 more point there. Okay, questions on that one?